Boa tarde a todos, sejam todos bem-vindos a mais uma live do canal do Museu Joias da Natureza. É com imenso prazer e alegria que eu estou desenvolvendo essa live em plena sexta-feira. É uma live especial, como várias outras especiais que nós temos aqui no canal do Museu Joias da Natureza, falando sobre crateras de impacto do Canadá, com o maior especialista em crateras de impacto do Canadá, Dr. Gordon OSINSKI, e com a mediação de dois outros grandes cientistas, a doutora Natalia Hauser e o Dr. Uwe Reimold, que é um dos maiores pesquisadores do mundo de crateras de impacto. Ambos estão na UNB, na Universidade de Brasília, então agradeço imensamente a atenção, a gentileza de todos vocês estarem aqui nessa live. Para mim é um grande orgulho, porque é a primeira live do Dr. Gordon OSINSKI aqui no Brasil. Espero que seja a primeira de muitas. E eu realmente estou muito feliz. Antes de começar a apresentação, eu quero agradecer também a todos que acompanham o nosso trabalho de divulgação e educação científica, que nós precisamos, num país chamado Brasil, de muito apoio nessa área. Quero agradecer ao nosso parceiro, o IPBio, que é o Instituto de Pesquisa da Biodiversidade, pelo apoio às nossas lives, e a todos os amigos que estão aqui nos acompanhando, tanto nas lives quanto nas exposições que nós desenvolvemos, até na busca de novos parceiros para reabrir o nosso museu, se Deus quiser, o ano que vem, aí, quem sabe. Bom, agradecer a todos que estão participando da live e que depois compartilhem, divulguem essa live extremamente incrível sobre crateras de impacto. Bom, para a gente começar, Dr. Gordon, before we can start your presentation, please tell us about you. How long you like this geological area, like impact craters? Please tell me a little more about you, Dr. Gordon OSINSKI.
Yeah, for sure. Well, thank you for the introduction and for the welcome. And it's a pleasure to be talking to you all today. So I'm a professor here at the University of Western Ontario, which is in London in Canada. My background is in geology, and I guess it's almost coming up for 25 years next year when I came to Canada for the first time to start my PhD. And that's really where I started looking at impact craters. So I knew nothing about them until then. I did my undergraduate in Scotland, and we didn't get to hear about craters. But I arrived in Canada, and 2 weeks later, I found myself up in the Canadian Arctic looking at the Horton impact crater that I'll talk a little bit about today. And basically, I haven't stopped. I just was in the field a couple of weeks ago up in Labrador at another crater here in Canada. I now look at craters all over the solar system as well, with satellite data and through looking at Apollo samples as well.
Wow. Amazing, Carrie. Congrats for sure. And congrats for your amazing work to training the next Artemis 3, the moon expedition. Congrats. After you finish your presentation, I have two questions about this, okay? So, Natalia, Dr. Uwe, let's go to start the presentation.
Okay, so I'm good to start. Okay.
You can start, please, Dr. Gordon.
Okay, so yeah, good afternoon again, and I'm going to talk about cratering in general, but some of the impact craters we have here in Canada. So let's kind of start big picture, because I'm sure there's people who don't really know what craters are. So let's start big picture. If you look, up out of the solar system, you'll see lots of kind of different images, but I really like this one because it shows you, we've got our planets, but this also demonstrates that space is not empty. And so we have the main asteroid belt between the orbit of Mars and Jupiter. And then if you've got a good screen or good eyes, you might see lots of little dots closer in towards Earth. Those are what we call near-Earth asteroids or near-Earth objects. And then we have a comet kind of pictured coming in from the outer solar system as well. And so since, the day after the planets formed and continuing today on a smaller scale, things, comets, asteroids, bits of rock and ice have been striking not just the Earth, but all objects in the solar system. And of course, our nearest neighbor, the moon, is really a testament to this. You can look up the moon even without a telescope on a clear night and see that there are all of these pop marks on the lunar surface. And this is, there are literally thousands upon thousands of meteorite impact craters on the moon, some of them reaching up to 2,500 kilometers across.
Wow.
If we go to Mars, there's a lot of interest in Mars for the past couple of decades, and still is with the Mars rovers. A little bit harder to see, but also, a large part of Mars, what we call the ancient highlands, is also being subjected to intense bombardment billions of years ago. And then, of course, still today, there are impacts happening on Mars as well. We live in exciting times. There's robots exploring the far reaches of the solar system. And so, I think every object we get to visit and see a bit closer, we see the marks of these cosmic collisions. And so this is Ceres, which, only a few years ago, we got the first close images, and it's very moon-like. We used to consider this an asteroid, but it's definitely more like a moon, and we call it a dwarf planet now because of that. And then even little old Pluto out there, far outer reaches of our solar system. There are not too many craters, but hopefully you can see that kind of big pale circular feature in the center. There's still some quite large impact craters on Pluto. And so we now, I think, know that impact cratering is, one of the most common, one of the most ubiquitous, one of the most important geological processes throughout the solar system, even here on Earth. And so let's kind of start to zoom in on our own planet. This is one of the first images ever taken of the Earth, from space. And you might look at this and think that, well, there's not a lot of impact craters. Asteroids and comets, don't strike the Earth, although not very important. But we do actually now know of, 250 locations on Earth where we have evidence for an impact. Sometimes this is a crater. Shown in green here are also kind of deposits where, they were formed by an impact event, but we don't have any idea of the crater or any record of the crater left. If you're interested in exploring this impact record of Earth more, you can go to impactearth.com. This is a website that I run with a few others, and we have a database of impacts and lots of other activities and things as well. And if you really wanted to get into the nitty-gritty details, we published a paper a couple of years ago, or just last year, that kind of goes into this in lots of detail. Just quickly, a bit of a history, because I don't really know this when I came to Canada. Again, it'll be 25 years ago next year, which is incredible for me to think. Is actually thanks to this gentleman here, Carlisle Beals, who was the Dominion astronomer of Canada. So we actually have an astronomer to thank here in Canada for really recognizing in the late 1950s the significance of impacts. And he started this quest of exploring Canada through air photographs, first of all, for potential impact sites. And so that kind of led into this database that I was just showing you. So if we zoom into Canada, we are a pretty big country, but the geology is such, there's a lot of ancient rocks here in Canada, which means a lot of the impact record is preserved. And we have about 31 confirmed meteorite impact craters going up from the high Arctic all the way out to Nova Scotia on the East Coast. And I'm going to talk about a few of these today, and I'm going to frame it actually in specific craters, but also hopefully show you how studying these craters here in Canada have helped us better understand how certain features of cratering occurs. And first of all, we'll talk about complex craters. So what are complex craters? Well, if you go to the moon, you can, where craters are a lot better preserved than here on Earth, we see this progression going from the top left round clockwise to the bottom, where the morphology, so the shape of impact craters, changes as you increase the size. And on the bottom right is Euler crater, and that is what we call a complex crater. So it's no longer bowl-shaped, but the walls have collapsed inwards, and we have this literally a mountain in the very center of the crater that we call a central uplift. But, how does this form? How does this process occur? Unlike volcanism and other aspects of geology where you can go witness the process happening, thankfully for us, we haven't witnessed the big impact event. So we have to start with the products and kind of work backwards to the process. So the moon is great for looking at what fresh craters look like, but as a geologist, there's nothing I like better than going out and looking at the rocks in the field. And so that's what we can do here in Canada. And first of all, we're going to take you to the Horton crater up in the Canadian Arctic. And this is where, I got my first introduction to cratering, again, all those years ago. So this is a really beautiful site. It's actually in a polar desert environment. So there's hardly any vegetation. This is a Landsat image that is about 30 kilometers across. And hopefully you can see this bullseye-shaped feature. The pale material in the middle is not snow or ice, but it's actually rocks that were melted by the impact. So these are impact melt rocks. This is a simple, may look complicated, but this is a simplified geological map of Horton. And for this kind of part of the talk, I'm just going to talk about all of these black lines. So these are faults. And so these formed when this crater went from this bowl-shaped depression to form this complex morphology. And if we kind of zoom in, well, what do we see? Well, we actually see surfaces like this. So this is taken from a helicopter.
Wow.
Looking at the walls of a valley. This is this landscape, which is kind of more Mars and Moon-like than Earth-like up in the Canadian Arctic. But if you can kind of see, there's a slightly shiny faces along these cliffs. And if we actually zoom in, and that's a very younger me in the bottom left, these are actually fault plains. And so this is one of the rare examples on Earth where we have really beautiful exposures of the faults that were created by impacts. And on the right-hand side is a zoom in. We call it, if there are any geologists on the call, we call these slicken side lineations. So this is what happens when you have two blocks of rock moving past each other. And so this has helped us, build up this idea that the walls of these craters collapse along a series of faults in the rim region. Excuse me.
Amazing landscape, Dr. Gordon. Amazing.
It is
wonderful
a beautiful
place.
landscape. Yeah, absolutely. Okay, so that's another high Arctic crater that was only discovered about 10 years ago, certainly hidden for a long time because it's quite subtle. So Horton is a well-preserved crater. This is the Tunnunik crater, which you can see it okay, I think, in this digital elevation model. So red is high and yellow, and then down to blue is lower elevation. But it's still quite, if I toggle this back and forwards, it's still quite a subtle feature, and it's been heavily glaciated. But what this crater has going for it, so it's kind of a plateau. It's another Arctic landscape. But there's this amazing river that is cut down right through the central uplift of this crater. And we just have this kind of spectacular scenery in Tunnunik. So there is a person at the bottom of this valley for scale. So these cliffs here are about 100 meters high, very large. But you can see here the rocks that were originally flat lying, like you would see in the Grand Canyon, but they've now been tilted by the force of the impact, as essentially this mountain has been formed in the center to create a central peak. As we go down in scale, we start to see features here. This is only a few tens of meters high. And, as geologists, we can start to map on how the complex deformation has occurred. And we can see this kind of down and down. And so, excuse me, and here there's actually a rock hammer there in the bottom right. And you can see how complexly deformed these rocks are. And so, impacts are actually fun from a structural geology perspective because you're forming these features in, a matter of seconds or minutes. As geologists, we're used to, dealing with processes that go on over millions of years. And here we have a very complex process that is done and finished in a matter of minutes. Okay, I apologize. My voice isn't great because I'm just getting over a bout of COVID, so I'll be taking a few drinks throughout this call.
No problem.
But thankfully it's good enough to present today. Okay, impactites. So this may not be a term you're familiar with. These are rocks that are generated or have been affected by an impact event. And so to showcase some different types of impactites, I'm going to take you up to another iconic crater here in Canada, which is this one. There's actually two craters side by side. These are these east and west Clearwater Lake structures. Maybe just to quickly go back for fun, a lot of people think this big arc off Hudson's Bay, I don't know if you can see my cursor, is an impact, but many geologists have looked at this region and there is no evidence. But we do have these couple of really prominent craters that you can see very clearly from space. And here you go, up on the top left there is a satellite image. So this is West Clearwater Lake. It's about 36, the lake is about 36 kilometers across with this prominent ring of islands. On the bottom right of that image, you can see a bit of the East Clearwater Lake structure. And this was a fun expedition we did a few years ago. Like many of the craters in Canada, they're very hard to get to. So we have to fly in. This case, it was a float plane. And we landed there and spent a month kind of exploring this crater, which hadn't been visited since the 1970s. And one of the really amazing things about this structure that I didn't expect when we went there is almost a complete sequence of what we call crater fill impactites. So these are the rocks that have been formed by the impact and that line the inside of the impact crater. And you go from bottom left, kind of going up and up and up, and I'll show you some kind of close-ups of some of these. But just kind of quickly, so we have, kind of fractured, brecciated, broken up rocks. C are these really interesting breccias where we have melt that was intimately mixed with non-melt material. All of the rocks at West Clearwater too have been oxidized, so there's a lot of hematite, iron oxide. That's why you have this kind of quite vivid red color. And then we go D, classed rich melt rocks, and getting classed poor as we go to the top. But I'll show you some big images now. And again, just a spectacular landscape. We're lower in the Arctic here, so there is a little bit of vegetation. Here's a rock hammer, and this is a big cliff of these, what we call classed rich melt rocks. So we melted, several cubic kilometers of rock because of the energy of the impact was so high. And what we find is that at the base of this melt layer is very class rich from kind of rocks settling out. And so the white features here are all clasts, fragments of rock, and then the red is that melt rock material. So there's just huge expanses and outcrops of this material. You can just see the teeny end of a pencil here. So this is a zoom in, and we see these really, I think, quite beautiful breccias where all of the red here is stained by hematite, but it really picks up nicely what was a glass. So this intimate kind of mixing as this material is moving around the crater of glass, the melt, and then just broken up fragmented material. Wow. Just for scale here, this kind of scree slope is probably a good 150 meters. There's quite a steep scramble up, and then it's capped by this cliff. And it's hard to kind of grasp the scale of things, but I've highlighted two things in red here. So these are actually fragments of rock that are, the one on the left, probably 2 stories high. Right, so this is, a big building that the size, 100 meters by maybe 50 meters that was just tossed around by the energy of the impact, and it's surrounded by actually impact melt. And we zoom in, it'll give you a better idea. So the 2 clasts are here on the left and the right. And if you've got good eyes, we can kind of zoom in. And in the middle here, I'll just go back, is columnar joints. So these are cooling joints, just like you would get in a lava flow. And we also see those in impact melt rocks as well. And we can kind of keep zooming in, and we can literally put our finger here. So here the clast is actually above, and it's surrounded on all sides by this impact melt. So, you know, this Canadian crater, Clearwater, was visited in the 70s. Some of the early papers on impact melt rocks and breccias were done here. And, you know, it's a site where I think we need to go back and visit more, because there's so much, you know, so much of this material over, you know, 50, 60 square kilometers. Okay, and so the next segment, I'm going to show you more impactites, but I'm going to take you to another crater where actually I just came back from again, up in northern Labrador. And so this is the Mestastin or Kamastastin in Innu lake structure. So this is quite typical for Canada, where a lot of the craters are in the Canadian Shield, these very old rocks, and they're like partially filled in by a lake. So here we have the image here is there's a scale on the bottom left. This is from Google Earth. We have the central peak that is still preserved at Mestastin. This is a crater that's only about 35 million years old. And so that peak that we get in the center of a complex crater is preserved, a lake around it, and then you can't really see the rim because it's been eroded. This is probably one of the most kind of iconic places I've ever visited. Which Grieve, a good friend and colleague, had a great kind of black and white photograph in a paper from 1975 where he first looked at these rocks. But now we have this amazing drone image, and that cliff is actually 80 meters thick, just the cliff, and that is impact melt rock. So it's an igneous rock that has all the features of an igneous rock. And again, you can see columnar joints here, beautifully displayed in this big cliff.
Dr. Gordon.
Yes.
This is the Discovery Hills?
This is the famous Discovery Hill locality.
Wow.
Yeah.
Amazing place.
Yeah. So we used to think that this was actually part of the crater interior, so part what we call the impact melt sheet. But in recent times, we've been working on it, and we actually feel that we're in the rim region of the crater. And so to give you an analogy, this is an image from a Japanese spacecraft, a beautiful oblique image looking at the rim of Tycho crater, which is about 100 kilometers in diameter. And you can see in the rim region of these craters, all of this blocky, what we call ballistic ejecta. So that's the ejecta that's thrown out early. But we then see these smooth deposits, and all of this black material we interpret on the moon as being impact melt. And so this, if you close your eyes and look back to Discovery Hill, this is where we would put this that structure at Mestastin. Just go back in one of these pond terrace regions. So this is really neat because this makes this impact ejecta. And if we actually zoom in, so here's another perspective of Discovery Hill. Again, you can see those beautiful vertical joints, which are cooling joints. But we're now going to zoom in on the far right here, where the melt overlays this white material. And one of the amazing features of Mestastin is this contact. And here we have this impact melt rock, which is overlying this melt poor, melt free ejecta. So this is actually one of only two places on Earth, the other one being the Ries crater in Germany, which Natalia and Uwe will know very well, is another complex crater where ejecta is preserved. And we actually see this same sequence of melt-rich material overlaying melt-poor or melt-free material. So again, we're very lucky in Canada to have a lot of craters, a lot of beautiful exposures. Many of these craters have not been studied in any detail since they were first discovered in the 1970s. So I think there's still lots and lots of work to be done.
Wow.
I'm going to skip over this because too many words and things, but some of this knowledge from Mestastin has given us this idea of ejecta emplacement being a multi-stage process. Okay. So I'm actually going to kind of, the final segment or the final topic is perhaps more surprising to people. If I asked you to think about, what would you think of if you picture an asteroid hurtling towards the Earth? It's probably, quite negative thoughts. You want to get out of the way. And we do know, from the Chicxulub impact in Mexico, that, asteroids are very destructive. But some of the work we've been doing at the Horton crater in particular, and quite a few people now have been doing elsewhere, it turns out that impact craters can actually be quite beneficial for microbial life. And so I'm going to finish on this really fun topic. And, so maybe not creating Eden, but at the very least, we have this hypothesis now, which is that impact craters can create, or maybe did create, conditions suitable for the emergence of life, either through substrates, the delivery of, carbon and other molecules through the carbon-rich meteorites, and the production of habitats for life. And I'm just going to focus on this last one in the interests of time. So after a crater forms, again, we actually, turns out, generate a lot of habitats that were never there before the impact. Crater lakes you may have heard of. Even the glasses that are produced during impact events can be quite ideal habitats for life. But I'm just going to focus in on the one now, which are hydrothermal systems. So hydrothermal quickly comes from the two Greek words, hydros and thermos, so heat plus water. If you have anywhere in the Earth's crust where you have a heat source and water, you can generate hydrothermal activity. So if you think of Yellowstone National Park, Iceland, I don't know Brazil well enough to know if there are active hydrothermal springs and things in Brazil, but these would be hot springs, hot pools and things where water is heated up, usually from a volcanic heat source, and then comes to the surface, and we get these really interesting environments for life. So we're going to go back to the Horton crater now. This is the satellite image again. But I'm going to show you a simplified geological map that I did way back for my PhD. And the main features I want you to look at here are just all these red symbols. And so these are areas around the crater where I've mapped out hydrothermal deposits. And you'll see that actually it's not random that we get a concentration of this hydrothermal activity kind of around the edge of the melt layer in the middle, and then in the rim region as well. So what does this stuff look like? What's the evidence that we had hydrothermal activity? Well, this is one of the most kind of interesting features. There's a rock hammer here for scale. We would call this a vug. It's kind of like a geode where you had this cavity, this hole in the melt rocks that were quite hot still. Fluids came up and then they started to crystallize out minerals on the surface of that void. The kind of sparkly green mineral here is marcasite, which is iron sulfide, quite just like pyrite. You've got a bit of rust here. You've got some calcite and other carbonate minerals. And then this quite interesting mineral, jarosite actually, is this yellowish material that we find on Mars, which is quite interesting too. Now, because this formed in the melt rocks that were produced by the impact, we know that this wasn't here before the impact. And so this is telling us that the heat from the impact and the interaction of water after the impact created this big hydrothermal system. We also have beautiful big crystals of selenite, so a transparent gypsum. Not as big as the crystal of Cayos in Mexico that you may have seen pictures of in National Geographic, but these crystals can reach several tens of centimeters, even a meter across.
Wow.
The other thing you need for a hydrothermal system, of course, is a network of fractures for fluids to go from one point to another. And as you might imagine, impacts are very good at fracturing the rock. And so around the edge of the central uplift, we see these veins of calcite. So the pale mineral here above the Swiss Army knife is calcite. And then last but not least, it doesn't look like much in the field to look at, but you'll hopefully see the arc kind of orangey iron oxide stains running down the cliff face. And these are, we interpret them as fossil, so ancient hydrothermal vents. So putting all of this together from Horton and other craters, we built up this kind of picture of a hydrothermal system in a complex crater. And so, it's quite interesting. There's different settings in a crater. We think this is actually quite relevant for Mars, particularly for the Perseverance rover right now, which if you follow what this mission is doing, Perseverance landed in Jezero crater in the crater floor, where it encountered a bunch of lava flows that came in afterwards, but it's going to make its way to the rim. And this is exactly where at Horton we see evidence for these hot springs. And so we're actually hoping that maybe this rover on Mars will encounter some of these deposits, which if you go to places like Yellowstone, we know are really quite interesting for life. And so to come to more of a kind of schematic, my kind of closing message here is that, far from being just solely agents of destruction, being very destructive processes, meteorite impacts might be very important for the search for life on Mars, and may have been even where life on Earth originated in some of these hot spring environments. We had a crater like this on early Earth with a lake, these steam vents, and these hot springs forming. These would have been absolutely ideal habitats for life. And if you're interested in this, we did publish a review paper on the role of meteorite impacts and the origin of life a few years ago. It's freely available online, so you can just kind of Google that as well. And I think I will end there, and hopefully I've left plenty of time to take any questions, and I'll happily discuss anything we've presented today.
Okay. Thank you very much. I will take out your presentation for we can speak a little. So thank you very much for your presentation, Dr. Gordon. For sure, I have some questions, but first, Natalia, Dr. Uwe, please, you want to ask something?
Thank you very much for this very interesting talk. You touched on a large number of topics. Obrigado para sua interessante apresentação, com muitos detalhes sobre diferentes tópicos. In your opinion, what are the most important fields in the studies of impact craters and impact cratering studies that should be attacked in the future? Or do we know everything? I think you said already that we don't.
No, for sure, yeah.
Desculpa, em português, quais são os mais importantes tópicos que precisam mais ataque, mais investigação no futuro, na disciplina de estudos de crateramento de impacto? Good.
Yeah, no, thank you, Uwe. A great question. I think, the reason why I think I stay interested, and perhaps you do too, is, there's still a lot to learn about impacts. There's, it's a part of geology that has come on, later. I'd say it's really only in the last kind of 2-3 decades that, the study of impact craters has really entered the mainstream. I'd say it's only kind of, again, recently that, at the undergraduate level in university, people are starting to, really think about the importance of impacts. Well, I mean, there's quite a lot we still don't, I would say, fully understand. The nitty-gritty details, the mechanics of how craters form, especially these complex craters, I think there's still work to be done. On impact ejector emplacement, I think there's still some outstanding questions there. I think I'm most excited about this kind of what happens after an impact. I would again say a lot of work has gone into understanding the destructive aspects of impacts, driven by Chicxulub, but wanting to understand the extinction of the dinosaurs and, mass extinction events. But I think it's, again, even more recent that we're starting to think about impacts from this, being positive. at least for microbial life, you know, on early Earth, maybe on Mars and other planets as well. And so there's not a lot of people looking at, you know, these hydrothermal systems and impacts. I'm one of the very few. And, you know, there's still lots we don't understand there. You know, how big a crater do you need to generate this? How long do these systems go on for? Is there evidence for life in these systems? And so there's, I think this is an area, particularly as we're exploring Mars with rovers and bringing back samples, that would be really great to look at in more detail.
Okay, thanks. Obrigado.
Dr. Gordon, I have one question. Gabriel is a friend of mine, and he studied meteorites and other things. Congrats for your presentation and your amazing research. I just want to ask a question. Here in Brazil, we have a few craters on basalt on Earth. Thinking about the early, more basaltic-rich Earth surface, what do you think it could be better target to rock to provide the better hydrothermal environment for the habitability for a fresh crater? So, the best sample that you think the target rock for this hydrothermal system? What do you think?
So, I mean, this is a great point, because, you know, I've talked about craters in Canada. We have lots of really great preserved ones, but we don't have any in basalt. And so that's where, you know, because of Brazil's unique geology, you have some amazing craters there formed in basalt, which, you know, does make them a better, I would say, one-for-one geological analog for Mars in particular, and probably early Earth as well. And so, yeah, you know, understanding how hydrothermal systems work and affect basalt, the types of minerals that are produced in those environments and in those rocks is definitely, yeah, an area where I would encourage more study of your Brazilian craters from that perspective, because they're very valuable as an analog for Mars in particular. Yeah.
Thank you. And he also asked, could the impact on basaltic rocks create the environment similar to you have found in Houghton?
Yep. I mean, I do think that there is some evidence. There's been, you know, a couple of papers published on Brazilian craters, and I've had a couple of students who've worked with Alvaro Costa, and they collected some samples. And, you know, we do see evidence of hydrothermal alteration in, you know, Vargem Dome, for example. But I think it needs much more study. More rocks, more study is definitely needed.
Okay. Natalia?
I think so that this Vargem and Vista Alegre, these two impact structure in Brazil, with this Schitzi and Meldingen, studying these hydrothermal veins, and he's doing the nice job. But sometimes we had the question, like, you know, I am thinking in Araguainia that the target rocks is mainly crystalline, and you have the sedimentary part, but still we are checking for hydrothermal alteration there. Still is maybe not the best example for the habitats in another planets, but it's interesting to see the relationship. I like so much the presentation, Gordon. Thank you so much. It's like to be in the field trip that I think so that they're amazing outcrops.
Yeah.
And I found out that was like a little difficult to go there, always by plane or by ship, or it's not so, you need to go in a special time on the year to these impact structures. And I had like a curiosity about this. What is more difficult to arrive in one of these impact structures that they are so far away, you know, from the cities?
Yeah.
It's a lot of preparation, I believe.
Yeah, it is. You know, I find it, you know, it's also part of I get a lot of, you know, joy out of exploring these craters too. You know, I get to go to a part of Canada where hardly anybody gets to go to. You know, very few Canadians go into the northern part of Canada because there are no roads. And so, it's an exciting part of, I've always loved exploring the outdoors. And so it's a lot of logistics, like you say, a lot of planning. It's usually by float plane or these twin otter aircraft on these big tires where we just land in the middle of nowhere. You got to like camping as well. We set up tents and, often roughing it for 2-3 weeks, but I enjoy that kind of thing still. And it's definitely part of, the allure, I think, of looking at these craters in Canada as well. Also a challenge, but it's a fun challenge.
Yeah. Gordon, another question, please. How important is it to training the astronauts for the future Artemis 3 mission to the moon in the impact crater site? And you choose the Mistacine crater for the rock, the anorthosite rock that you can find in Mistacine, like the moon. You can tell a little more about this expedition. Congrats for your NASA work. Amazing.
Oh, thank you. So I really think it's an interesting time for, our field of study, the study of meteorite impact craters. I've been told stories of how, and I've learned from others, and that, the Apollo, when we first went to the moon, that really spurred some of the first study of actually these craters here in Canada, for example. Before the mid to late 1960s, there weren't a lot of people looking at impact craters, but kind of Apollo missions actually encouraged a lot of the study. So I'm actually hoping that, because of the Artemis program, that, we'll get maybe a lot more younger scientists looking at impact craters again, particularly here on Earth, because there's so much to do and learn. Because we look at the moon, and like I said at the very beginning, there's really only two main processes that have shaped the surface of the moon: volcanism and impact cratering. And in particular, the South Pole region of the moon, where we're going to go with the Artemis program, it is this heavily cratered environment. Everywhere the astronauts will go, they'll be seeing rocks that have been affected by impacts, ejected by impacts. They'll be exploring craters. So it's really important that we train not just the astronauts, right, but it's everybody in the geology of meteorite impact craters, the managers and mission control, the engineers, everybody. And so, I think it's an exciting time. I hope it will raise the profile of people looking at impacts even more so. And it turns out that here in Canada, we have this great analog for the moon, because it's not basaltic, but the major rock type of the lunar highlands, that white material that you see, on a clear night, is anorthosite. So quite like granite, that kind of coarse-grained igneous rock, but without the pink potassium feldspar. So it's made mainly of plagioclase feldspar. And Mistacine is one of the few craters in the world that formed in a large part of anorthosite. And so at that crater, we have not just those beautiful melt rocks that I showed, but, ejecta deposits of this anorthosite material up the central peak. Part of that is formed of anorthosite as well. And so, I just returned a couple of weeks ago from taking 2 of the Artemis 2 crew there to give them some training. And we're hoping to take back, the next people who walk on the moon will hopefully have been up to the Mistacine crater in Labrador to study its geology, which is super exciting for me.
Wow. Yes, for sure. Anorthosite is a uncommon rock.
Yes. Yeah.
In Earth, but in the moon is much common. Dr. Uwe, you have some question more? Natalia?
Gordon, you and your team have been quite active in education, in outreach at various levels, school children, obviously students. It's your core job. But can you tell us about your activities? Because that's obviously interesting to anybody who's associated to a museum, like Paolo. Also interesting for many people in the universities because they all have a program here called Extensão Outreach.
Good question.
That's great to hear. Yeah, I've always I'm a university professor, so I deal obviously with undergraduate and graduate students. But I've also always had a passion for, going into schools, and the excitement of planetary science and impacts is something that I'm definitely passionate about. If you actually go to the website impactearth.com, we do have some resources there. I think one of the neat thing about impacts is that you can make it very fun for kids, even down to age 5 or 6. You can making craters is a really fun thing to do. You can do it in the classroom with, we use flour and then cocoa powder. You can spread that out, and you can just, throw things into it, and you'll form these super small impact craters. And, so even, they get to make a mess too, which is always fun as a child, as a kid. But you can actually turn it into quite a really good science experiment. They call it here in Canada, kind of North America, inquiry-based learning. So you're learning by asking questions, coming up with hypotheses, and then you can test them. And we have an activity where you can actually do that. So what happens if I go from a golf ball to a baseball? What happens if I change the height that I drop the ball? And, simple things, but you get the students in the classroom to think, predict what will happen, and then you can actually go and do the experiment. And so it's a really fun thing to do. The other thing I've been trying to do, and we did this recently with Paolo, was, even for universities is, most geology departments have, those nice cabinets of rocks and minerals. But probably not many have impact crater materials. And so, partly because I've been able to go to a lot of these Canadian craters, either permanently or on loan, I'm happy to share. I've got these rock kits and pelican cases that I've put together where they can go out to schools and museums and things on loan, to kind of, because again, seeing the actual rocks, being able to hold the rocks is much nicer than just seeing a photograph. And so, yeah, keen to see more of that. And I know you're doing some great work in Brazil, all of you on here, to do the same.
Yes.
Thanks, Gordon.
Thanks. I also have one question. About the possibility to find a new impact structure in Canada. You think is okay or difficult?
Well, I think
have a lot of.
I think it will be difficult, but I think there must be more craters still to be discovered, even here in Canada, that you think would be well studied. The main reason I always say that is because if you look at a map of Scandinavia, very similar rocks, 2 shield areas, rocks that are 2-3 billion years old. I think because Scandinavia is smaller, there's been a lot more detailed field work and mapping done. There's a lot of craters kind of per square 100 kilometers in Scandinavia. And if you took that same distribution in Canada, I think we should have more up there. They're just, I think, very inaccessible places where people don't go on the ground. We've probably found the easy ones from satellite images, but I'm certain there will be, there are more out there to be discovered. It's just, honing down the search. And then obviously, even if you think you've found one on a satellite image, you've then got to go there to collect samples, which can be a big challenge as well.
Yes. I already give a look at one place in Canada, Prince Edward Island.
Yeah.
You know something about this area, because I already know maybe could impact crater. What do you think about this?
It has been, if there's any evidence, there's none left. It's a bit like Hudson's Bay, though. I think Prince Edward Island, there's another kind of circular structure, a big bay, and then the island is kind of like banana shaped. But I think, all the geology doesn't fit with it being a meteorite impact. If it was, it would be giant, several hundred kilometers across, and we just don't see any evidence for it. Yeah.
Okay. Natalia?
I have one question about the numerical modeling, because it's really important to understand what's happening in the first, in the second, in the third second after the impact. But how much do you think that the numerical models today are close to the reality? How much they can reproduce what we see in the field trip, that we are seeing something like maybe it's not complete, was eroded or, or disappeared. So how much do you think that the numerical models are close to reality today, or what we need to do to improve them?
Yeah, great question. So I think they've come a long way, just even in my career, from 20, 30 of the last 20, 30 years now, the models are getting much more sophisticated, and I think are getting closer to reality, what we see in the field. We're not there yet. I think a big leap is going from that 2-dimensional modeling to 3 dimensions. I think that's very important, but that's very computer intensive, because, they are 3-dimensional structures, and in particular impact angle, I think plays a major role, particularly when it comes to kind of complex geology. You could argue an impact into the Canadian Shield that is nothing but, let's say, gneiss, a metamorphic rock, fairly homogeneous, but the craters I was showing where you got lots of sedimentary layers, the basaltic targets would be the same. You've got different rock types, planes of weaknesses. I still think there's more work to be done there in making the models more realistic. So yeah, come a long way, but definitely more work still to be done.
Okay.
But the important thing is, what do you put into the model?
Exactly.
Many field data, lab data
to
feed the modeling process.
Yeah.
Otherwise, in my opinion at least, it's just a model.
Yep. I completely agree, Uwe.
Yeah. Yes. Gordon, tell me, Canada have one of the most important economic impact crater is the Sudbury. In Canada, other important noble metals deposits like Sudbury, or this is a unique in Canada, in your opinion?
I think Sudbury is unique. There was a big combination of factors that came together kind of all in the right place to make Sudbury, one of North America's biggest mining camps. But there are others. Out in Alberta and Saskatchewan, for example, there's some craters that have been, at least historically, have produced oil and gas. A lot of craters have been, because of, you have this bullseye-shaped fracture network, and it's been really good place for oil and gas to accumulate. Everyone's kind of different. There's another one in Saskatchewan, Carswell, that is an active uranium producer. It's one of Canada's biggest uranium mines. There's some effect. The impact has actually partly brought the material closer to the surface, so it makes it more economic. But then through the hydrothermal alteration, kind of concentrated it further as well. So, Sudbury is unique, but there are other kind of, I would say, smaller examples that of craters in Canada that have been economic.
Okay. Dr. Uwe, more questions?
Are there any plans in Canada to set up geoparks and impact structures? That's a topic here.
Amazing question, Dr.
Yeah, I haven't heard much discussion, and I think it would be nice. A lot of them are very remote, but there are some like Sudbury that is very accessible. That I think could be an interesting conversation to have. So.
Dr. Gordon, please tell me why the Natural History Museum around the world don't have a lot of impact material in exposition. Why? Because it's so important, it's so nice, it's so different, the rocks. I love it. I completely love it. Why? For sure, in Brazil and other places, I think in Canada, I don't know, but you have this answer for this question, please. Why?
I'm afraid so I do not have the answer to that question. Why? I definitely would like to see more museums around the world have more impact material. Getting the material is difficult, but I think it's just, again, it's been a slow realization over the last few decades of the importance of meteorite impacts, not just geologically, but potentially biologically. And so, hopefully as, we move forward, more and more museums will have more and more material.
In Canada,
not every museum, sorry, Paolo, not every museum has a Paolo Mattioli.
Yeah. Yep, you need to champion people who know what they're talking about too. Yeah.
Thank you for your reference, Dr. Uwe. For sure, I in the next year, if I open my museum, the most large, I think, impact collection on Brazil, I think one of the most around the world. I have now more than 150 different samples from different craters around the world. And for sure, a lot of help. Dr. Natalia, Dr. Uwe, Dr. Gordon, also Dr. Christian Kobel, Dr. Álvaro Crosta. I have helped a lot of friends, the scientists around the world, because I think it's so important, this geological area. And nobody know. When I ask in Brazil, do you know Brazil have like 90 impact credit? Yes. I don't know. Yes. But I speak with geologic students, not the society. So for this reason, I think it's so important you have this material in exposition, also in museum and the other places too. For sure, in Canada, I remember the Royal Ontario Museum that I visit since time ago in 1998. I give you a look at some nice samples from Sudbury and the other craters too. But I think Vienna have a very nice museum. And in Berlin, Dr. Uwe can tell me, my Berlin have an amazing collection. And just no more. So the rocks is very nice. It's very beautiful. Dr. Gordon, you send me the shutter cone, is amazing sample. Why? This is the question that I would like to, maybe that you told me, nobody know this area.
Yeah, I think that's a big part of it. Absolutely. Yeah. Hopefully that will be changing.
Yes, I hope so. Natalia?
Okay.
Dr. Uwe, some questions. You have always good questions.
I'm not having a question anymore, but I hate to be a little bit pessimistic because we were really interested, or our generation, and Gordon is rapidly coming up to that age too now. We were fascinated by space exploration. We became very interested in impact. What about the next generation of students, of graduates, and teachers and museum curators? Are they going to be interested by the new wave of space exploration that is coming the next couple of years, or is it going to go past them? I think we need to work very hard while we still can to make sure that this interest does not disappear?
I 100% agree, and I certainly hope that with Artemis and going back to the moon, that there will be lots of excitement. So let's hope so.
Me too. Dr. Gordon, one last question, please. My son, Petrus, would like to know how many different impact craters you know personally in Canada.
That I've been to, or that
yes.
I know about?
No, you've been to.
Oh,
you visited.
I probably should know off the top of my head, but I don't. But it's probably getting close to half of them now.
Yes,
I would say so. Yeah.
And you research how many? You study how many?
Most of the ones I've visited, I would say I either have studied in the past or I'm studying now. And we actually have this new collection. Quite a few of the Canadian craters are buried, so there's not much to see on the surface. But we do have drill core from some of these craters now here at Western, and I'm starting to look at those even as well. So, I will never. Well, there's nothing to see if you visit some of these craters, but at least we have some samples and starting to work on those too. So hopefully when I retire, I'll have looked at them all. We'll aim for that.
Other structure outside to Canada, like USA, Brazil. I know that you never have been, but USA, some Beringer crater maybe.
Yep. Yeah. I mean, there's I've been to quite a few craters around the world. Beringer crater and a few other craters in the US. There's some great ones in Europe, Australia, and I've done some field work in those kind of two locations as well. Yeah. Okay. But not Brazil, but hopefully that will change.
My friend Marcelo who have a question. At least there is upsurge of interest in space, so maybe it's not a total loss for humans. So space astronomy, a lot of people like it. Maybe you can how can I say, the impact crater, you can put together the same knowledge because it's so important, like you training the astronaut inside in the crater, in the structure. Like the Eugene Shoemaker made this in the Apollo,
Well, I totally agree, and that's a great kind of positive note to end on, isn't it? But, let's hope so.
Yeah, me too. So, Natalia, a gente, para finalizar nossa live, mais alguma questão, Dr. Gordon? Okay, Dr. Uwe, more some question for we can.
No, I think I would like to congratulate Gordon for the great work he's doing in Canada and other parts of the world too. And thanks very much for this presentation today.
Thank you, Uwe.
It was a fantastic presentation and was glad to be in the field trip.
So, Dr. Gordon, again, thank you very much for this presentation. Wonderful about impact crater. I love it, Thank you very much for your time. And before we say goodbye, tell me some words about what do you think in the future, not just about this geological area like the impact crater, but the science, because in Brazil it's so hard to study, to research, and you have the museum, the Natural Museum. The creation is so difficult to work in Brazil because you don't have financial support and other things. But tell me some positive words. What do you think about the next future, including the visiting to the moon, to the Mars? What do you think about the science, the planetary science, mainly?
Yeah, well, I think you already said it, so I'll just re-emphasize it. But I think we have an opportunity. We will all have to work hard at it. But just like with Apollo, I think with Artemis, with the prospect of sending, humans back to the surface of the moon, there's going to be a need for more scientists, not just, to help train the astronauts, but to look at samples as well. So there's definitely a need for understanding the cratering process better, getting more people interested in it, into planetary science in general. And so, I think we need to make that link between why the study of craters is important for going back to the moon. And I think if we can do that, then, it will be exciting, and we'll hopefully research in Brazil and elsewhere will be easier and more, easier and more profitable to do.
Thank you so much. So, now I say goodbye. Natalia, muito obrigado. Muito obrigado por você estar aqui comigo, ter feito a mediação, estar aqui junto. Eu agradeço muito a sua parceria. Dr. Uwe, muito obrigado. Vou falar em português agora. Muito obrigado, Dr. Uwe. Excelentes perguntas. Fico feliz de ter você também como parceiro do museu, assim como a Natália, o Dr. Álvaro, enfim. Para mim foi um grande orgulho ter vocês nessa live. Dr. Gordon, thank you very, very much for your kindness, for your scientific support, collaboration. I hope that we can meet someday to go together, maybe in Araguainha. I invitation you, please, the next year, maybe, who knows. But thank you for the samples. I hope that in the next future we can make other exchanges or other trades. So I think today for me is a wonderful day. I stay with the three most beautiful scientists in this area that I love it. So thank you very much, Dr. Gordon. Have you a nice weekend. And you, Natalia, Dr. Uwe, have a nice weekend, and we talk more later.
Okay, thank you so much.
Bye.
Bye now. Have a good weekend.
Bye, Dr.
Thank
Ciao.
you. Ciao.
Ciao.